All right, so full screen looks good. So this video is going to be about the completing the square process, where it comes from, significance, why we use it so much. It's another fancy term for putting quadratics in graphing form. Ax minus h squared plus k form. That's really about completing the cube. Okay, and of course, this is in the category of quadratics, which are four-sided figures. Quad in Latin meaning four. And one of the first things you learn in early algebra is how to factor, because it's a quick and easy way to get zeros if something can be factored. And what does it mean? Length equals zero, width equals zero. Well, they're dimensions, right? And if your width is zero, there goes the area. It's gone. And if your length is zero, there it goes. Bye-bye. So that's why you learn how to, do x minus 7 times x plus 3 equals 0. Then these numbers as input 7 and negative 3 get us the 0. 7 minus 7 times 7 plus 3 is 0. Minus 3 minus 7 minus 3 plus 3 times gets us 0. Big. So it's an important skill. We use it in lots of places in math. Now, what happens if the 21 minus 21 all of a sudden became minus 23? Well, I don't think it's quite so easy. It's not easy. Can't find those user-friendly numbers. So what evolved mathematically? Well, somebody probably looked at this and went, well, that's a rectangle. That can be written as x times x minus 4. And so maybe we can reconfigure that. Let's see, maybe I need a little more space here. So let me do that. So I'm not bunched. Right? Somebody saw this as x times x minus 4 minus 23. All right, then they said, well, okay, so what can I learn from that? Well, I can see a couple of table values. I can see that if I put a 0 in, 0 times anything is 0, well, I get minus 23. Now I can certainly see that if I put the number 4 in here, that gets rid of the width, gets rid of the area, and 4 gets me minus 23. And people must have, once Rene Descartes got his coordinate system up and running, plotting the 0, 1, 4, 9, 1, 4, 9, that nice cup-shaped graph, right? Certainly going to get one here as well. The dominant term is going to get us a cup-shaped graph. Rise over run squared as measured from the vertex. And if I've got a 0 here, and a, what was it, 4? Oh yeah, positive 4 over here. Getting me minus 23. Getting me minus 23. And if I follow that down, I'm on the decreasing side. There's an indicator as to which side your y-intercept is on. In this case, it's on the decreasing side. But what's most salient here is this x value. And it sure seems to be right in the middle of these two numbers. 4 and 0. When I say numbers, I'm talking about the x values. Well, that would give me a 2. And if I want to find out what I get when I put a 2 in, well, I got a couple of calculations. Why don't I use this one here where I can actually see the area generated? 2 times negative 2 is negative 4. And negative 4 minus 23 is minus 27. All right. Now, one thing that I push on day 1 in my algebra 1, algebra 2, and pre-calculus, and sometimes calculus classes, is the templative situation here. I wish the heck we would never, ever talk about mx plus b again early on in a math class. People think that every graph, some students think every graph has something to do with mx plus b, and simply not true. I wish we reorganized to this template, and the a term of each is geometrically found. All right, this one, rise over run, everybody's familiar with that. But the a term of a quadratic is actually rise over run squared, as measured from H, the vertex. So let's do that over here just to show you that we're going to get the number 1 in front of x squared. How do I get from, here's 2, negative 27. How do I get from negative 27 to negative 23? I actually go up 4. That's my rise. How do I get from 2 to 4? I change by 2. But I said we have to square that. If you go over 2 units, that's the linear change. The quadratic change is squaring that, and it gets the job done. I'll do another one of those for you quickly at some point in the video. All right, but let's continue on with this notion of completing the cube, because why does that help us? Why does it help us to reshape? Oh, I never did reshape it yet, did I? Okay, so x minus 4 minus 23. Okay, and I'm going to reshape that into a square. Why? Because I can solve most equations in math using inverse operations. Why can't I use a square root on this? Sides of the rectangle aren't the same. Can't do that. But what if I make them the same? What if I take this longer, what appears to be a longer side is really shorter, this longer side, and I tack on a little bit over here and reshape this. And if I did that, I would get x minus 2 times x minus 2. Of course, that doesn't give me x squared minus 4x. That gives me x squared minus 4x plus 4. But if I want to make the areas the same, I can get rid of this 4. I got a marker. And if I bring in minus 23, I think I got this in graphing form. I think I'm seeing x minus 2 squared minus 27 equals 0, which was our goal, was to solve this for 0. I can bring the 27 over. I can divide by 1. I don't have to in this case, but I want to show you that. I can undo squaring with square rooting. Remember, cup shapes have 2 answers, positive and negative side of H. And these are real answers, so this thing should have graphed it. So x, what was it? 2 gets me minus 23. And I'm trying to hit minus 27, sorry. And I'm trying to find when I hit this graph hits 0. All right, and so what do I have here? I have x minus 2. I've got it right up here. Okay, and so minus 2 becomes positive 2. All right, so let's actually drop our answers in. Let's forget that multiplication by 1. 2 gets rid of this number, which is good because it doesn't take me to my destination, numerical destination. 27 plus minus the square root of 27. Let's see what happens here. Oh, the 2's cancel. Squaring a plus minus gets me this square root, and squaring that square root gets me 27, and 27 minus 27 is 0. So I'll do 2 more. One with a coefficient that is greater than 1. And I did put this here for a reason. So let me go back to this. I forget exactly what I had, something like that. So in my class, I allow everything. I don't like to see minus 4 doing the same thing to both sides. I don't think it trains the mind the way it needs to be trained. So subtract 4, everybody should be able to subtract 4. Right, 7 plus 4 is 11, and 7 is equal to 11 minus 4. So what do I learn from that? Addition on the left, subtraction on the right, and that holds true with all the operations. So the 4 is gone, multiplication by 5 is division by 5, so now we're at 3. 3 times 7 is 20, I'm not doing that yet, sorry. The inverse of E, ln of 3. Now I'm going to multiply that by 7. You can really do this in one line of work. You multiply that by 7 and then add 3. And I ask my students to get a feeling for the ln of 3. It's about 1.1. And we've got an exact answer here using inverse operations. Well, that's why we're completing the square, so we can use inverse operations. And we get good at it if we practice it. Now, how do I complete the square for something with a coefficient other than 1? And then I'll do the general case. So let's look at 2x² plus 20x minus, I don't know, how about 15? Let's get that to equal 0 using completing this. Well, it's a little trickier because I'm really going to factor out 2 times an area of x² plus 10x. So I'm really doing that, completing the square there, and that is equal to 2 times x plus 10 minus 15 equals 0. Can you see this? You can. Yeah, I captured everything. All right, and so what do? We reconfigure this to be 2 times. Now we make a square out of this. And so we've got a 0 and a -10. So -5 is what's important. And I'm going to do this here in a moment. So -5, so this is x plus 5. And I'll have to put x plus 5 here. All right. And now what do we have? We've got x² plus 10x plus 25. So we have to get rid of that 25. And we already have minus 15 here. Running out of board space. Right, and so now I've got the same thing. So I can move that minus 25 here. Right, and minus 15. I should have the same calculation here. All right, so let's throw a number like 2 in here, just random number. 2 plus 10 is 12. 2 times 12 is 24 units of area, times 2 is 48. 48 minus 15 is what, 33 units of area? Let's put 2 in here. 2 plus 5 is 7. 7 squared is 49 units of area. 2 times 49 is 98. Minus 25 is equal to 78 minus 5 is 72. Minus 10 is 62. Take away another 5, and I'm not getting the same answer. Means I got to do the video again. I didn't double this change, so it's worth doing that. That's my mistake. I won't do the video again. So I got to double the change here. And that's part of the mathematical process, is when your brain gets tired and you goof up somewhere, you got to go find out where. I found out where, right? Because I don't generally do completing the square. You know, I use minus b over 2a, which is what I'm going to get you in just a second. All right, so 2 times minus 25 is minus 50. I've got to include that. Minus 50 minus 15. And 2 times this is 98. So there's your 98. There's your 48. Minus 15 is your 33. All right, so there is definitely a process here that I botched. But let's do the general form. So let's take ax² plus bx plus c. Now let's see where a few things come from. All right, so there's your rectangle. All right, what can we see? We can take out what's common, which is x, and that leaves us ax plus b, and we've got plus c equals 0. Well, what can I see from this? I can see, let's pretend a is positive. Let's say it's a cup shape up. I can see 0 gets me c, and I can see that minus b over a. Ax plus b equals 0. Subtract b, divide by a. Right, and if I plug it in there, minus b over a, I hope you can see the inverse operations. All right, so minus b over a gets us c, and what's in between those? Well, what would be in between 2 and 10? You add them up and divide by 2 and get 6. So if you add these up, add it up that way, up, already getting ahead of myself, and divide by 2, lo and behold, minus b over 2a appears to be the average of the roots. Right, because it doesn't matter what constant I had, I could have had a 0 here, right, and that would have been a 0, that would have been a 0, and that's the average of the roots, minus b over 2a. It centers the quadratic. So how would I then more quickly graph something like y equals 3x² minus 30x plus 7. First, I know it's cup shape up. I know I'm on the decreasing side. I know a 0 gets me 7 here. You could do that as a last step. And then I just do minus b, 30 over 2 times 3 is 6, so that's a 5. And I plug 5 in, and here's the nice thing about plugging 5 in. When I get 75, this is always going to be twice that and opposite. Whatever this is, that's got to be twice that and opposite. I'll show you why in a second. Plus 7, and that means I can get negative 75 plus 7 shortcut, minus 68, I believe. Minus 68. Let's do a quick a equals rise, the change in y over the change in x squared. All right, as measured from the vertex. So 5 to 0 is 5 units of change, but 5 squared is 25. So there's the run. Negative 68 to 7 is up 75. And 75 divided by 25, lo and behold, is 3. Must be a nice coincidence. All right, so that's a quick graph. And of course, I got my roots immediately. What are my roots? Well, where do I hit 0? They're real. Hey, what do I have to do? I got to go up 68 units, but if I multiply by 3, I got to undo that. And if I square that change, then I got a plus minus, and I'm measuring from the number 5. Why? Because I could have easily put this in graphing form, x minus 5 squared minus 68 with an a term of 3, and you solve that. Bring the 68 over, divide by 3, undo the square, with square plus minus square rooting, minus 5 becomes positive. And we can show that here with our answers. It's good to see it once in a while. 68 over 3, what happens to the 5s? Cancel. What happens to plus minus when you square it? It's positive. What happens when you square a square root? Disappears. What happens when you multiply by 3 and divide by 3? The number doesn't change. And 68 minus 68 is 0, and we're done. All right, now, why did I say we have that 2 to 1 ratio? Well, if I make a square out of x minus 5 and x minus 5, let's put the x minus 5 this way. Minus 5, well, let's call that x squared. And that's minus 5x. And that's also not looking like a square. Let's make it a little longer. So we have some like terms. Minus 5x. And we get a constant here. Yes, k, constant for cat. So we put 5 in, that's 25. That's the quadratic term. Minus 5 times 5 is minus 25. And another minus 25 down here. And I can see that linear 2 to 1 opposite relationship. And that always happens at the x value of the vertex of a quadratic. It's a pattern. And you always want to keep your eyes open for patterns like these. Okay, if we didn't have mx plus b, right, we could have a kind of a standardization. So what's the conversion? The conversion of a is really x minus h to the 1, because that's to the first power. This one is really x minus h squared. That's what cancels. This one's a little more complicated, and I'll do that one last for you. All right, so let's do a linear 37 to 823. So we're measuring linear change from 3. I'll put the 1 there. That's linear change from 3 with an initial condition of 7 at that x value. How do I change? 8 minus 3 to the 1 is 5 to the 1. Get that out of there. How do I go from 7 to 23 up 16? I rise over run squared. All right, so how do I get that equation? Well, I measure square change with an initial condition of 7. Square change from 3. And if I put 8 in, 8 minus 3, get squared in order to cancel. Now, how do I get from 7 to 23? Oh, I think I had 16. This one's a little more complicated, but I'm measuring cubic change from 3 with an initial condition of 7 units when x is 3. And if I'm going down at 10 to 1, right, then my a term is actually the cubic change from 3. 8 minus 3 is 5 cubed is 125 units. I know I still want to go up 7 to 23. I know I still want to go up 16 units, but this term over here throws everything off. 8 minus 3 is 5, so negative 50, I have to counteract that with positive 50, and that should be that cubic. And if you want to know more about cubics, then you got to look at a whole bunch of videos. And well, once you get a handle on it, a couple of days of looking at it, then you can visualize cubics and their rates of change. This m term is c minus 3ah squared, as measured from the point of inflection, and the cubic videos go into that. So you can have some fun with that if you're trying to dive into this stuff more deeply. All right, so I hope I did some justice to the cause. So completing the square allows us to solve any quadratic. Right? It's not necessarily the quickest and easiest way, but it certainly is a friendly way. And we use completing the square at other places, like, which I really haven't done, but I'll do a circle for you real quick. Just to show you that, you know, this technique gets used in lots of other places, conic sections in particular, but comes into play solving various equations. So let's just look at x squared minus 8x plus y squared minus plus 10y. Let's get a different one. Let's go 25 and 4, 9, 29. Let's go plus 20. All right, so x minus 8x, x squared minus 8x could have been written as x minus 4 squared minus 16. And this is just a quad. A squared plus b squared equals c squared. All right, a, b, c. A, B, C, Pythagorean relationship. There's your a squared, there's your b squared, there's your c squared. And as one of these variables changes, the constant area never does, so we get this rotation. All right, y plus 10, y plus 5 squared, minus 25 equals 20. So here's our graphing form, x minus 4 squared plus y plus 5 squared equals 49, and you got a circle centered at 4, negative 5, 4, negative 5, and a radius of 7. Right, and there's your triangle, there's your x minus 4 length, there's your y plus 5 length, and this is a Pythagorean relationship. And if I put in the number 4, I have no width. So everything would come from the 7 units above. And if I put in a negative 5, I have no height. Everything would come in from the horizontal. And we get that rotation centered at 4, negative 5. Okay, so using this stuff in one place often leads to using it in another. And I hope that maybe helps somebody. And camera looks a little blurry. Hope that came out all right. And have a good day.